I hope is there.
Yeah, can you see my slide?
We could, but then they disappear for some reason.
We see your slide, yes.
Okay, so
yeah.
we can see it again. Okay, so you're the Koji from Keio University, and is going to be speaking about convolution, CNNs. So,
okay, thank you very much, Javier. Yep. And I'm Koji Fukagata from Keio University. It's nice seeing you all, although online. When the camera on the back was on, I could see the room of the Newton Institute, but unfortunately, I cannot see that. Anyway, my talk today is entitled Application of Convolutional Neural Network to Turbulence. As you know, we are now in third AI boom. Yeah, thank you very much for turning on the camera. And there is an increasing attention for the machine learning everywhere, accompanied by attention to the big data and the deep learning techniques. And also, as you know, turbulence is a high-dimensional nonlinear dynamical system producing a bunch of big data. So turbulence big data should be suited for machine learning. And it has become easier to start machine learning of turbulence big data due to the development of algorithm, library, hardware, and information site, and so on. And application of machine learning to turbulence has a relatively long history. Already 20 years ago, researchers like Chang-Hun Lee and Komosakos attempted to use machine learning for turbulent drag reduction and flow estimation like this. And we see many studies recent years, and to my feelings, research that seem to be a lot in the last few years, like estimation of aerodynamic coefficients, some alternatives to conventional CFD, like physically informed neural network and EDM, reduced order modeling, turbulence modeling, and control. And actually, application of machine learning has also been investigated in my research group under these JSPS projects. And our aim is to apply machine learning to turbulence big data, extract nonlinear features, and find their governing equations. And finally, to propose a new flow control method based on extracted features. And this is a basic structure of the machine learning model we are mostly using. The network structure is basically CNN autoencoder. The flow field, although it is lambda, flow field is low dimensionalized by the encoder part of the CNN encoder, autoencoder, and the part in the middle does some operation depending on the purpose. And the flow field is recovered from the low dimensional latent vector using the CNN decoder. And in this example, the middle part is drawn with a multi-layer perceptron, but this part can be replaced by something else depending on the purpose. And here is a major outcome, which can be roughly classified into the development of surrogate model and estimation of lagged information. And today, I will briefly introduce some of these results. In the first example, we attempted a direct regression of flow fields at 2 consecutive time instants in a turbulent channel flow. Here we pick up YZ cross-section, cross-sectional field, and we want to construct a surrogate model to reproduce this dynamics from the cross-sectional information only. And actually, this is a streamwise velocity fluctuation. The red is high speed, blue is low speed. And this is a network structure to learn the relationship of the cross-sectional velocity field between 2 discrete times n and n+1. And the network structure is basically similar to CNN autoencoder, but in this case, the input is time n, the output is n+1. And the correct answer is given by DNS data at n+1. In other words, this network is a surrogate model for time discretized Navier-Stokes equation. And this slide shows the prediction using the trained network. Once the initial condition is given by the DNS data, the network recursively predict the field at next time step with the input at time step n, which is already predicted by neural network. This is the correct answer obtained by DNS, and these are the prediction by machine learning. Case 1 and case 2 differ from each other in terms of the latent vector size. While case 1 produces quite similar structure to DNS, including high and low speed streaks, case 2 with a smaller latent vector size cannot capture the small scale structure. And this is turbulence statistics. Although I will omit the detail, these are, sorry, it's quite small to see, URMS, VRMS, WRMS, PRMS, and Reynolds shear stress, stringwise vorticity fluctuation RMS, and these are span-wise spectrum of stringwise velocity. And case 1 to 4 differ from each other in the structure of machine learning model, like the size of a latent vector and the number of multi-layer perceptron layers. But anyway, as we have seen in the animation, case 1 did the best job. And this is a temporal spectra and temporal two-point correlation. And the agreement is very well. And in the case of machine learning, actually no spurious oscillation like this, which was originated from the periodic, very short, sorry, in this case, this is 2 pi delta perhaps, periodicity in DNS box. What we do here is actually to, sorry, I will go back, to train the relationship between n and n plus 1. We are not doing, we are not training the whole sequence of time development, but we are just training the relation between n and n plus 1 so that we can remove this kind of spurious oscillation. And the trained network can be used as a turbulent inflow generator in turbulent simulation with inflow and outflow condition. As you know, the conventional technique used for inflow and outflow simulation is to run another driver DNS in a periodic domain. But this machine learning model can replace this driver DNS with much lower computational cost and obtain turbulent statistics in the downstream main simulation region is in good agreement with the conventional method. And please note that an improved version based on so-called GAN has been reported by Chan-Hung Lee's group after our work. And next example is to use CNN autoencoder for low dimensionalization and to use so-called long short-term memory, LSTM, for its temporal prediction. We have applied this network to flow around black bodies as well as a turbulent channel flow. While this network can reasonably well predict the flow around a body of untrained shapes like these, for untrained Reynolds numbers, prediction fails in some cases. And in the case of turbulent channel flow is also reasonably well predicted like this, but further improvement is needed to reproduce more detailed dynamics. Anyway, this is a network structure used for turbulent channel flow. We used a 3-dimensional convolutional neural network and different lengths of LSTM layers to capture different time scale and different spatial scale. Then once we can low dimensionalize the flow field, we can also derive the governing equation for the low dimensional dynamics. This is an example of the flow around the circular cylinder with some transient. In this case, we can low dimensionalize the flow field into only 2 variables like this, and we can derive a nonlinear ODE for low dimensional autoencoder mode using a technique called SINDI, proposed by Steve Branton. We have also confirmed this technique not only for the simple cylinder flow, but also for the 9-equation turbulent shear flow model. And once the governing equation like this is mathematically expressed, it is also possible to combine it with a modern control theory, for example, to stabilize the vortex shedding like this. By the way, what is obtained by the low dimensionalization using CNN autoencoder? We consider again the flow around the circular cylinder and low dimensionalize the flow field into two variables like this. And also to visualize the contribution of each variable, we decode each of variables separately like this. And this network we call MDCNN AE. This slide shows a comparison of velocity field reconstructed using the first modes obtained by different techniques. POD is a conventional linear method. MDCNN is our neural network. And actually, MDCNN linear has the same structure as MDCNN tan H, but all the activation function was set to be a linear mapping in this case. And upper figure shows an instantaneous field of the streamline velocity, and the lower figures show the time averaged error as compared to the reference DNS. As we can see, the reconstruction result by POD and MDCNN linear are quite similar, and the error is very much similar each other too. And the error is much suppressed in the case of nonlinear MDCNN. The same can be observed for the vertical velocity component. And this result suggests that the CNN autoencoder is basically similar to POD, and the nonlinear activation function included in the network works to improve the reconstruction with the same number of modes. Next, to see what is contained in these two modes obtained by nonlinear CNN, we apply the POD to the collection of reconstructed field. I will skip the detailed explanation, but it has turned out that the single nonlinear low dimensional modes contains multiple POD modes, so that a better reconstruction for the same number of modes is possible with nonlinear CNN. We have also confirmed the function of the nonlinear activation function. Here we consider the problem of estimating the higher order POD coefficient A3 to A6 from the first POD coefficients A1 and A2 in a cylinder flow. In fact, in this problem, it is known that A3 to A6 can be expressed by the nonlinear functions of A1 and A2. And we want to confirm whether this kind of nonlinear relationship can be captured by the nonlinear neural network. And the result shows that this nonlinearity cannot be captured by the conventional linear estimation methods, but it can be properly captured by neural network. The similar thing have been observed in channel flow example. Here we try to estimate the velocity field in a turbulent channel flow from the wall shear information only. And we compare our machine learning model denoted as nonlinear CNN with some linear methods like LSC and linear version of CNN. And as far as a reconstructed vertical structure is concerned, the LSC looked to give a closer result to DNS, but quantitative examination reveals that the estimation is better with nonlinear CNN. Although non-dimensionalization by CNN autoencoder works well for a simple problem like a cylinder flow, we need to improve this compression ability towards its application to turbulent flows. One of the ideas we tested is so-called hierarchical CNN autoencoder. In this hierarchical CNN autoencoder, the first subnetwork is trained to reproduce the most important feature of the flow. And after that, the second network is trained so as to capture the remaining feature and so on. For the flow around the cylinder, this hierarchical CNN AE achieves higher compression than the conventional CNN AE, while 3 POD modes were included in one nonlinear mode in the case of conventional CNN. With this hierarchical autoencoder, 8 POD modes are contained in just one mode. So we can expect higher compression also for turbulent flows. And this is a result when the hierarchical autoencoder is applied to turbulent channel flow. And actually the reconstruction by hierarchical autoencoder is slightly better than POD and CNNA conventional autoencoder, but this error is still high. 0.28 means 28%. And we still need about 2,000 or 3,000 moles to reproduce the field with the error level less than 10%, like this. And from now, I will quickly introduce some examples on the estimation of lagged information. The first example is a super resolution of flow field. This is the instantaneous vorticity field in a two-dimensional decaying turbulence. And with our machine learning model, we can recover this high resolution field from this 4x4 super low resolution like this. The input is like this and the output is like this. And the same technique was also applied to a spatial 3D plus temporal super resolution. And we have confirmed it works well. And we can also reconstruct the entire flow from the limited number of sensors like this. In this example, we use a so-called mixture density network to output the estimated mean and estimated standard deviation at the same time. And by doing this, we can estimate not only the entire flow field, but the uncertainty of the estimation. And this is another way of quantifying the uncertainty. In this case, we collect the weights in the last step or last 100 or something steps of the training, and we collect the weights by assuming the Gaussian distributions. By doing that, we can quantify the standard deviation due to some distribution of the weight. And this is a case of cylinder flow example, but we have also tried to some other flows. And all the examples so far were limited to the application using numerical simulation data. But of course, we can apply the similar technique to experimental data. And in this example, the network is trained using DNS data, but in its use, we feed the, sorry, there's no figure here, but experimental particle images to obtain the velocity field. And it works well, even if there is a region where the particle image is missing like this. And investigation on the weight inside the trained network revealed that the upstream CNN layer, like here, tends to focus on the geometric information of the embedded body and missing region. And downstream CNN layer tends to focus on the flow characteristics. And finally, we have also extended similar techniques to deal with unstructured data using voluntary tessellation. In this case, we have put a finite number of sensors, and we divided the areas using voluntary tessellation to relate to sensor information and the area where this sensor is responsible. And also we feed the sensor location information as an image like this. And by doing this, I will skip here, we can reconstruct the flow even if the sensor locations moved, or even if the number of sensors are changed from those used in the training. Okay, to summarize, all the examples I showed today are basically just fitting, which read like this in a case of autoencoder. But this can become a powerful tool for example, further understanding of physics using smaller number of variables, and cost or data amount reduction of float predictions, and application of advanced control and optimization theory through low dimensionalization. But for further utilization for turbulent research, further low dimensionalization and clearer interpretation should be necessary. And finally, I would like to acknowledge my former and current students and all the collaborators. And according to the participant list, I think Kai Fukami is sitting in the room. So please ask him if I cannot answer your question. Okay, thank you very much.
Thank you. But assuming that you can answer your question, is there any question from the audience? Yes.
Yes, thank you for that. This maybe a comment, maybe a question. So if I understood the cylinder work, you always left the Reynolds number fixed. You didn't try and extrapolate in Reynolds number. Is that correct?
Yeah, in the example I showed today, I didn't show any example with different Reynolds number, but in the case of flow around the circular cylinder, we tried different Reynolds numbers. And in this case, when the trained Reynolds number and tested Reynolds number are different to each other, in some cases it worked well, but in some cases not. The machine learning fails when the flow regime drastically changes.
Yeah,
like
so
Reynolds number 40 yeah.
My recommendation would be that you try to explicitly learn the mean flow as well as the oscillations, because it's pretty well understood that there's a strong mean flow modification as a function of Reynolds number.
Right.
And if you look at Noak's work and other people's, anyway,
Yeah.
that's just
okay.
comment.
Thank you very much. Yeah, thank you very much.
Okay. Other questions? I do have a question. I mean, at some point you were trying to understand what the CNN was thinking, which
yeah,
of course is an interesting thing. Okay, and you did that by comparing the results. You say, well, if I change this, the results change. And I mean, assuming that you don't know the results, is there any other way of guessing what this machine is doing, or this monstrosity is doing, or whatever?
This is a very difficult question, and I think people in the machine learning in fluid mechanics are annoyed by the same question. Do you have any recommendation or any idea?
Yes, I have a question.
One thing we did is to compare with the linear theory, of course, like POD. But yeah, I'm wondering if there is any other method to interpret what machine learning is doing. Yeah, we have to think about that.
Okay, thank you.
Yeah, thank you very much.
So if there is no other question, let's thank Koji again and all the speakers in the session.
Thank you very much.